Welcome back to Calculus 2. We're continuing our look into series, our introduction to series. We're going to start out by looking at a simple theorem. This theorem gives a very basic property about convergence or divergence of a series. It says, if the series converges, then the sequence must converge to zero. Now, it doesn't go the other way. It is not true that if a sub n goes to 0, then the series has to converge. It is necessary that that happens, but it is not the only condition that has to happen for a series to converge. But the other way, if it's not there, it's certainly this is not true. And that's actually where our useful theorem is going to come from. If not this, then not this. But the proof of this is pretty simple. If you think about if this converges, then this equals some sum s, which is the limit as n goes to infinity of the sequence of partial sums. So we just say then, okay, s sub n equals a sub 1 plus a sub 2 plus dot 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 plus a sub n. And then let's say s sub n minus 1. S sub n minus 1 would be a 1. I'll go ahead and add the a sub n minus 1 term. So plus a sub 2 plus a sub 3 plus dot 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 plus a sub n minus 1. So now let's look at what s sub n minus s sub n minus 1 is. Well, just do term by term. Everything's going away except that a sub n term. So, if I now take the limit as n goes to infinity of a sub n, because we have to show this goes to 0, well, this equals the limit as n goes to infinity of s sub n minus s sub n minus 1. And we know we can split the limit between those two, limit as n goes to infinity of s sub n minus limit as n goes to infinity of s sub n minus 1. And we know this goes to s. And so does this. I mean, it's the same sequence. It's just a term behind, but it's still going to the same place. So s minus s, well, that's just 0. So we've actually proved then if this converges, then the sequence has to go to 0. So that's the proof. Probably could have typed it up instead of drawn it, but I don't know. I find proofs are better if you discover them in the doing. So our useful result from this is that logically, the way if-then works is if you contradict this, it contradicts this. So if a sub n does not converge to 0, then the sum of a sub n does not converge. And that's what the theorem on the next slide says. This is called the nth term test for divergence, which is a very useful, mainly just because of how simple it is, test for divergence. So you can see here, contrapositive of the previous theorem, the nth term test for divergence says a series diverges if the limit of its sequence is not 0. Anything but 0. So if it diverges, certainly the series diverges, but also if it converges to some finite number that's not 0, still diverges. If you look at the term-by-term sum series, so a sub n plus b sub n each term, and sum that up, you can split the sum between them. So this, the term-by-term sum, will equal the sum of the a sub n's plus the sum of the b sub n's, and thus a plus b. And the difference is true just like that. And you can also factor a constant out. If you want to prove this, it really just comes from looking at the sequence of partial sums and then just using the rules of algebra. We know for any finite number of terms with a common k, we could factor out the k by the distributive property. So it extends to an infinite amount of terms. And as a last statement before we move on, there are a couple of corollaries of these properties right here. So notice it said convergent. Then this is true. If either one of those are divergent, so you have a convergent series and a divergent series, if you sum or difference them, they're both going to diverge. Also, if you take a constant multiple of a divergent series, unless your constant is 0, it's still going to diverge. If your constant is 0, I mean, it's just going to take the whole series to 0, so it's not going to diverge, but it's not going to do much interesting either. Alright, that's all the theory for this section. Let's do some exercises. So our first problem we're going to look at, it deals with geometric series. We have a difference of two geometric series here, a term-by-term difference. It says write out the first 8 terms to show how the series starts, then find the sum of the series or show it diverges. The first 8 terms, that's going to be 5 over 0. 5 over 2 to the 0 minus 1 over 3 to the 0, so that's 5 minus 1, plus 5 over 2 minus 1 over 3, plus 5 over 4 minus 1 over 9, plus 5 over 8 minus 1 over 27, 2, 3, 4, plus 5 over 16 minus 1 over 81 plus 5 over 32 minus 1 over 243 plus 5 over 64, getting close, minus 1 over 729 plus 5 over 128 minus, I don't know what 3 to the 8th is. 3 to the 8th, that'd be 21, 21, and then 3 times 30 is 90, so minus 3 is 87. 2187 minus 1 over 2187. Alright, that's a lot of terms. Well, I guess we can do this. These should both be convergent geometric series, and we know if they're both convergent by the theorem we just looked at, you can just split the sum and find their sums individually. So this would be the sum of 5 times 1 over 2 to the n from n equals 0 to infinity. And that should match up just fine. Minus the sum n equals 0 to infinity of 1 over 3 to the n. So this should be 5 over 1 minus 1 half. Because it's a over 1 minus r, I think is the... Yeah. If r is less than 1, you could plug into this. Minus... in this case, a is just 1, so 1 over 1 minus 1/3. So that's 5 over 1 half, which is 10, minus 1 over 2/3, which is 10 minus 3 halves. 20 minus 3 is 17 halves. So it sums up to be 17 over 2. So use the nth term test. Now note, if we get 0 from doing our limit, we will say inconclusive. But if we get anything other than 0 for our limit, we will say it is divergent. The nice thing about this is that you can ignore the series and you're just looking at the sequence. It only tells you whether something diverges or not, but if it tells you that, it is very handy. We'll look at several tests for convergence or divergence in this chapter, and this is pretty much the simplest. So if I look at n goes to infinity of that, I mean, you can multiply it out if you want. I note just the top's going to have n squared plus n. The bottom's going to be n squared plus 5n plus 6. But just because the top and bottom are equal powers, I can just do this trick. Divide top and bottom by the biggest power on the denominator. And then you get 1 plus 1 over n on the top, and 1 plus 5 over n plus 6 over n squared. Then everything goes to 0 except the 1's. So 1, not 0, diverges. Because the nth term test said if it went to anything but 0, it diverges. Now, don't think the series necessarily has to converge if it goes to 0. It doesn't. But it definitely diverges if it goes to something other than 0. I know I've said that before. It's something you need to hammer in because it's something you can forget. So this, if you do the same trick, divide top and bottom by n squared. Although you really don't need to. 1 over n. 1 plus 3 over n squared. Limit as n goes to infinity. It's not really equal. This term equals that. But this will go to 0. Because the top will go to 0, bottom will go to 1. So what does that mean? Well, that means this is inconclusive. Because the only time we get useful information of the nth term test for divergence is when we get something other than 0 as our limit. So if we were going to definitively state whether this was convergent or not, we'd actually have to do another test. I think this actually still diverges, if I remember correctly. I think you could show that with one of the other tests. This is a tricky one. I think I'm going to do my trick I did with polynomials on top and bottom and divide by the biggest power on the bottom. That will get me 2 over 4 to the n plus 1 over 3 over 4 to the n plus 1. This instruction is considerably more vague, but certainly we can still use the nth term test if it applies, and I think it will in this case, because if you take n goes to infinity, this goes to 0, this goes to 0, and then I have the 1, so this is going to go to 1. That's not 0, so diverges by nth term test for divergence. Let's see if we can make this work. So on the top, we have n to the n. So 1 over 1 plus 2 times 2 over 2 times 1 plus 3 times 3 to the third over 3 times 2 times 1, 4 to the fourth over 4 times 3 times 2 times 1. Let's look at the sequence. Because we have n times n times n times n dot 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 times n times n of those, and then we have n times n minus 1 times n minus 2 times n minus 3 times dot 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 times 2 times 1. Well, this is just 1. All of these are greater than n over 1 because n over n minus 3, n over 2 is multiplying it, yeah. Yeah, because n over 1 gets multiplied by n over 2, which is larger than 1, by n over 3, which is larger than 1, all the way up to the first thing that's not larger than 1 is n over n. So that's greater than that. And then this limit as of n goes to infinity of n over 1 is infinity. So this has to go to infinity as well. So this diverges. So series diverges by nth term test. For divergence. This is by no means the only test, but it's the only one we have right now. So, in this problem, we're looking at a geometric series with an unknown in it. A variable just can represent any real number, but we're asked to find all values of x for which this will converge. We'll find in a later section that this can actually be considered a function where it converges, and then the set of x's for which that will happen and will be the domain. But that'll be much later in the chapter. For right now, they're just asking, what can we plug in for x and still have this series converge? Well, this is geometric in its very setup, so if we use that form, well, this is n equals 0 to infinity. They're both in the same exponent, so I can basically multiply them together, so that'll be negative x minus 3 over 2 to the n. And I think I'll go ahead and multiply that negative through, so that'll be 3 minus x over 2 to the n. Sum from n equals 0 to infinity. My exponents still match up, yeah, for using the geometric series formula. So I do need 3 minus x over 2, the ratio in absolute value, to be less than 1. That's where it's going to converge. Oh, it said also find the sum. I'll type that in here. So first off, if that's true, then I'm going to multiply off the 2. Absolute value of 3 minus x is less than 2. So that means the distance between 3 and x has to be less than 2, which just based on that, just subtract and add 2 to 3, you get a 1 to 5, but we can actually solve it. 3 minus x less than 2, greater than negative 2. Because remember, that's how you remove an absolute value. Subtract the 3's, negative 5, less than negative x, less than negative 1, divide by a negative, 5 and 1, and remember, dividing by a negative flips inequalities. So, domain of this thing is 1 to 5, so that's the values of x for which the given geometric series converges. And as for what the sum is, well, we just plug in a over 1 minus r, so a in this case is just 1. 1 over 1 minus 3 minus x over 2. Multiply top and bottom by 2. 2 over 2 minus, that minus will distribute through, so minus 3 plus x. So that'll be 2 over x minus 1. So that's the sum wherever it converges. And that'll finish up this video and our introduction to series. In the next video, we will look at our first test for convergence or divergence. We'll look at the integral test, which the main thing to keep in mind with most of the tests for convergence or divergence is the assumptions you have to have for them, because some of them are pretty restrictive, but the integral test is a nice test. Thanks for watching. See you in the next video. Have a great day.